Hi, this is Jonathan Gardner. This is the third section of Ohm's Law 711. And this one where he starts off, he has a long discussion where he talks about why we're not following Newton's first law here Newton's law where the sum of the forces equals m times the A vector. So he starts off with the idea of you have a car that has to travel through town and he has to stop at stop signs everywhere. It doesn't matter how fast your car is. The average velocity you get is actually related to the square root of the acceleration, which is still not quite what we want. So then he drops that model and says, what if we had a bunch of things that are bouncing around against each other with a small amount of drift? How long would it take for these particles to move a certain distance? And there he gets a formula that does give you some constant times the force applied to it. His comment is that this formula that he derives is not really what's going on. There's when you get into the quantum mechanics of what's happening, it makes a lot more sense. So one of the things that we do when we study circuits and fields and stuff like that is we make this assumption that this is a big assumption. Okay, that we have are basically a perfect conductor. That means there's no voltage drop across wires. Okay, that's not true. We know that you can grab any wire and you can measure the resistance of the wire. You can measure the voltage drop when you put a current through it. But it's a very good assumption, and especially when you drop in your resistors and they're kilo ohm or mega ohm resistances, it makes the resistance drop across the voltage drop across wires meaningless. For all intents and purposes, the voltage at one end of the wire is the same as at the other end of the wire. Another thing is that we get this equation equals VI, or you can rewrite it as I squared R. That's just substituting V equals IR for V. This is called Joule heating law. This tells you how much work is being done to move the current through a resistor or through a section that has a resistance. And finally, he gives this little formulation that's kind of cool. So he says the power is equal to the force dot the velocity unit volume. Okay, well, we can just do rho v. That's the current density. Well, the current density is just sigma times the electric field, so that's E squared. Okay, and so this is an interesting derivation where we say that the power that is consumed in a field is proportional to the conductivity and the electric field, right? So the more you got going on there in terms of the potential difference across it and the resistance will give you the power that is consumed there. So anyway, that's the end of section 711. Next is we're going to cover some electromotive forces, talking about why the current happens to travel the same speed throughout a circuit, which is kind of fun, and we're going to have a somewhat different vision of what's going on inside of circuits than our electrical engineer buddies. So thanks for your time. Take care and goodbye.